Hello students, in this video we'll be talking about how to draw the structure of oxo acids containing two central atoms. Let's get started with the examples. Oxo acids are those molecules which contain at least one hydrogen atom, one nonmetal and one oxygen atoms. But these oxo acids also might contain two nonmetals or three nonmetals for one molecule. So oxo acids can be classified into two types. The molecules which contain one nonmetal such as HNO3, HNO2, H2, SO4, etc. And on the other hand, the oxo acids which contain more than one nonmetal like H4P2O8, H4B2O5, etc. In the last video, which is part 2 of P block elements, we already have discussed how to draw the structure of oxo acids containing only one nonmetal. And in this video, we'll be talking about how to draw the structure of oxo acids containing two nonmetals. Alright, so let's get started. Whenever you have to draw the structure of oxo acids containing two nonmetals, there are a few things that you need to know in advance, of which one is oxidation state. You need to know what exactly is oxidation state and how to calculate oxidation state of the given atom and what is the maximum group oxidation state of that particular atom. So if you don't know any of this, nothing to worry. I'm going to have a quick brief introduction done to all of these topics. First of all, oxidation state is nothing but the apparent charge present over any atom. If you are talking about Na+, in Na+, there is a charge of +1. So +1 is oxidation state of sodium. Similarly, if you are talking about C-4, in C-4, there's -4 charge on carbon. So -4 is the oxidation state of carbon. In this way, the charge that you see in the power of any atom or a molecule or a species can be considered as oxidation state. Basically, this oxidation state arises due to either loss of electrons or gain of electrons. So the positive charge arises when the loss of electrons occur and negative charge arises when the gain of electrons occur. Which means basically the positive oxidation state and negative oxidation state can be seen in case of P block elements. So let us observe the group oxidation state or maximum oxidation state now. The electrons that are being lost or gained are of course from valency shell. So based on how many electrons do you have in valency shell, you can observe the oxidation state. For example, if you are talking about boron family is group 13, which means in the last shell of boron there are totally 3 electrons and you can remove all 3 electrons. And hence the maximum possible oxidation state of boron is +3. And after that, if you are talking about the carbon family, the number of electrons in the last shell is 4. So maximum you can remove 4 electrons from here. Hence the maximum oxidation state is +4. And for nitrogen, which is group 50, maximum oxidation state is +5. And if you are talking about oxygen, which is group 16, maximum oxidation state is +6, and halogens group 17, maximum oxidation state is +7. So these are the maximum oxidation states or group oxidation states of these elements. And in case you're talking about silicon, because silicon also belongs to group 15, even for silicon, it is +4. If you're talking about phosphorus, +5. If you're talking about sulfur, it is +6 because silicon, phosphorus and sulfur also belong to group 14, 15, 16 respectively. Okay? And I'm sure you know how to calculate oxidation state already. If you don't know how to do it, let me quickly give you the formula to do that as well. The oxidation state of any particular atom in the given molecule is equal to the sum of oxidation states. For example, in case you are talking about HNO3. In HNO3, to calculate oxidation state of nitrogen, you would have to take the sum of oxidation states of all the elements that you have here. You have hydrogen, its oxidation state, plus you have nitrogen. Since you don't know its oxidation state, consider this as X. Plus you have 3 oxygens, so 3 into oxidation state of all the oxygens. The sum of oxidation state of all the elements present in the given molecule is equal to 0. Remember, I'm talking about a molecule over here which is neutral. In case you're talking about a cation or anion, then the sum of oxidation states must be equal to the net charge that you have. So sum of oxidation state of all the elements or all the atoms present in the given molecule is equal to 0. For the given cation is equal to whatever cationic charge that you have for the given anion is equal to whatever anionic charge that you have. For example, if I ask you to calculate oxidation state of sulfur, the sum of oxidation state of sulfur, which I assume to be X because I want to calculate it, plus the oxidation state of 4 oxygens that I have must be equal to the total negative charge that we are having, which is -2, right? So for better understanding, let's take some examples to calculate oxidation state in this page. Calculate oxidation state of nitrogen in HNO2. Since you are calculating it for nitrogen, assume it as X. Hydrogen's common oxidation state is +1, plus X is for nitrogen, which we are calculating, plus 2 oxygen atoms, and each oxygen atom's oxidation state is -2. And because you are talking about a neutral molecule, the sum of all of these oxidation states must be equal to 0. And when you solve it, you have to solve it for the value of X. And when you solve it for the value of X, it turns out to be +3. So oxidation state of nitrogen in this molecule is +3. And in case you're calculating it for SO4 -2, as we discussed in the last page, it has to be X plus 4 oxygen atoms and each of -2 charge, which is altogether equal to -2. But why are you equalizing this to -2? Because there's a net charge on the molecule, and hence you have to equalize it to whatever charge you have over there. And when you solve it, it turns out to be X minus 8 is equal to -2, and hence X is equal to +6. Oxidation state of sulfur here is +6. I hope this gives you a clarity about how to calculate oxidation state. Anyway, going back, we are talking about how to draw the structure of oxo acids containing more than one nonmetal, containing 2 nonmetals basically, right? And in order to do that, you need to have a clear idea of the concept of oxidation state. You should be able to calculate oxidation states, and you should be knowing the group or maximum oxidation states. That's what we have revised in this page. Now, moving on to the rules. In order to draw the structure of oxo acids containing more than one central atom or containing 2 central atoms, let us be specific, you would be following a few rules. Of which rule number 1, you would have to calculate the current oxidation state of that particular element. Current oxidation state as an oxidation state in that given molecule. Okay? And rule number 2, or you can consider this as steps. Step number 2. Step number 2 is you need to observe the central atom and you need to check the central atom's maximum or group oxidation state. Check its group oxidation state. And then step number 3, you would have to compare the calculated current oxidation state to that of the group or maximum oxidation state. And when you compare, there are 3 possibilities. When you are comparing, possibility number 1 that you could see, the current oxidation state should be equal to the maximum oxidation state. This is one possibility. And possibility number 2 is current oxidation state being greater than maximum oxidation state or group oxidation state. Possibility number 3, the current oxidation state could be lower than maximum oxidation state. When you are comparing the current and the maximum oxidation states, these 3 possibilities can be observed. And now based on these 3 possibilities, you will identify the type of bonding between both the nonmetals. For example, if I am talking about a molecule which looks like this, H2X2O4. X I'm here considering as central atom, and X is like, just a schematic central atom. It is not halogen or something. Assume X is some unknown atom which is behaving like a central atom. And I calculated the current oxidation state of central atom. I calculated the group oxidation state of central atom. Then I compared. When I compare, if the current oxidation state and group oxidation state turn out to be equal to each other, then you might be having XOX bond. O refers to oxygen, X refers to central atom. If the current oxidation state is greater than the maximum possible oxidation state, then you might have a peroxy bond like this, XOOX bond. If the current oxidation state is lower than maximum oxidation state, then both the central atoms could be directly connected to each other. So this comparison step is helping you to identify the type of bond between the central atoms. If they are directly connected to each other, if they are connected to each other with the help of a peroxy group, or if they are connected to each other with the help of a single oxygen. Okay? And after you identify this, then you have to go to your step 4. And what is step 4? Step 4 is observe the number of hydrogen atoms, which will be equal to the number of hydroxy groups present. So you can follow these 4 steps or 4 rules in order to be able to draw the structure of oxo acids containing 2 central atoms in them. Okay? To understand it better, let us take some examples. Example number 1, H4P2O4. O6. So what is the first step that we would have to be doing? First step is identify central atom, calculate its current oxidation state. What is oxidation state of phosphorus in this present molecule? For that we have to consider what? We have to consider the rules to calculate oxidation state, which says that the sum of oxidation states of all the atoms is equal to 0 for a neutral molecule. So 4 into plus 1, oxidation state of 4 hydrogens, plus 2 into X. I don't know the oxidation state of phosphorus yet. I'm trying to calculate. So I assume this has X for now. Plus there are 6 oxygen atoms and each oxygen is minus 2, which is altogether equal to 0. Now you would have to simplify this and solve it for X. This will be 4 plus 2X minus 12, which is equal to 0. Which means X over here is equal to plus 4. So the current oxidation state of phosphorus in this molecule is plus 4. Done. Let us move now to the second step. In second step, you have to calculate the maximum oxidation state based out of group number. Phosphorus comes from group 15. It has got totally 5 electrons in the valency shell. So its maximum oxidation state is equal to plus 5. And then let's go to step 3. We have to compare the current oxidation state and maximum oxidation state. Current oxidation state is plus 4 from step 1. Maximum oxidation state is plus 5 from step 2. And when I look at the relation between both of them, the current oxidation state is lower than that of maximum oxidation state. And when you have this kind of thing, what kind of bond do you get to see? The current oxidation state being lower than maximum oxidation state, there is a direct bond between both the central atoms. So we get to know that there is a direct bond between both the phosphorus atoms over here. Done. And now let's go to step 4. And what is step 4 all about? Step 4 is about how many hydrogens do you have? We have 4 hydrogens in the formula, which is equal to 4 hydroxy groups. So 4 hydrogens is equal to 4 hydroxy groups. Alright. So you will be having 4 hydroxy groups in this particular molecule. Now using all of these details, let us draw the structure of H4P2O6. So according to step 3, there is a direct bond between both the phosphorus atoms. And according to step 4, there are 4 hydroxy groups. And whenever you have hydroxy groups, try to distribute them symmetrically. If it is not possible, then go asymmetric. Now that I have 4 hydroxy groups, I can equally distribute them. I can symmetrically distribute them. So 2 hydroxy groups to the first phosphorus and 2 hydroxy groups to the second phosphorus. And then other than whatever is represented already here, what else are we left with? We had 4 hydrogens, we represented all of them. We had 2 phosphorus, we represented all of them. We had 6 oxygens, we represented only 4. What about remaining 2 oxygen atoms? We can represent them connecting to each of the phosphorus units. But then when you do so, with the help of a single bond, oxygen's valency remain unsatisfied. To satisfy oxygen's valency, take a double bond. But then cross-verify if phosphorus can afford that valency or not. Phosphorus, each of the atoms have got 5 bonds, which is its maximum oxidation state. So phosphorus can exist in plus 5 state and hence your structure is correct. This is how you can draw the structure of molecules containing 2 central atoms or 2 nonmetals. Let's take one more example to get this better. The second example is H4P2O7. So this time you have to try and follow the instructions. So step number 1, calculate the current oxidation state. Current oxidation state. Step number 2, calculate the maximum oxidation state based out of the group number. Step number 3, observe the number of, step number 3 has to be comparing the current oxidation state and maximum oxidation state, and then go to step 4, observe how many hydrogens do you have and equalize it to the number of hydroxide atoms, and that's when you have to draw the structure. So if you already have tried doing it, observe and self-evaluate if your answer is correct or not. Since it is a neutral molecule, the sum of oxidation states is equal to 0, according to which I have 4 into plus 1 oxidation state of hydrogen and 2x for phosphorus since I don't know, plus 7 into minus 2 for oxygen. All of this together is equal to 0. And when you solve it, x turns out to be plus 5. So the current oxidation state is plus 5. And phosphorus belongs to group 15, so its maximum oxidation state is also equal to plus 5 because it has 5 valence electrons in the outermost shell. And when I compare current oxidation state and maximum oxidation state, both are plus 5, which means both are equal. When both of them are equal, what kind of bond can we expect? there should be an oxygen atom between both the central atoms. So between both the phosphorus units, there needs to be an oxygen atom like this. And in step 4, what do we have? The number of hydrogens is equal to number of hydroxides, right? So there are 4 hydrogens, which means 4 hydroxides. There are 4 hydroxide groups, and I'll be drawing all 4 of them in a symmetric manner. I'll give 2 hydroxides to first phosphorus, and I'll give 2 hydroxides to second phosphorus. And other than the atoms that we have represented, we still have 2 more oxygens left, and I'll be taking them with a double bond on each phosphorus. This way, when I check for the valency of phosphorus, each phosphorus has got 5 bonds, which is the probable suitable valency for phosphorus, and oxygens have got their double bond. So valency of all the atoms is satisfied, which says that your structure is correct. Let's now move on to the third and last example for this video, and this example, H4B2O6. H4B2O6. Follow step 1, calculate the current oxidation state of boron. Step 2, calculate the maximum oxidation state based on group number. Go to step 3, which is comparing both the current oxidation state and maximum oxidation state. Then go to step 4, identify the number of hydrogens, which is equal to number of hydroxides. When you follow these steps one after other in systematic way, it gets easy for you to solve the questions and draw the structures easily. So let's get started with the step 1. You're talking about boron over here, and when you solve it, boron seems to have plus 4 oxidation states. So 4 hydrogens with plus 4 and 6 oxygens with minus 12, which is altogether plus 4 oxidation state of boron. And maximum oxidation state of boron is only plus 3 because boron is from group 13. If current oxidation state is plus 4 and maximum oxidation state is plus 3, it means current oxidation state is greater than maximum oxidation state. And when you have such relation, what kind of bond can you expect? You expect a peroxy bond like this, oxygen-oxygen single bond between both the central atoms. So you'll be having a boron with the 2 oxygen atoms between. And then you have totally 4 hydrogen atoms in the formula, which means 4 hydroxy groups. Because I have 4 hydroxy groups, I'll be symmetrically distributing them. 2 hydroxy groups to first boron and 2 hydroxy groups to second boron. And other than whatever I have represented here, there's nothing else to show. There were 6 oxygens and I have represented all of them in the structure. There were 4 hydrogens and I have represented all of them in the structure. There were 2 borons and represented them in the structure. So this is the structure of H4B2O6. So using this method, you can draw the structure of any oxo acid containing 2 central atoms. But as I told you in the second part of this series, there are some exceptions for all these shortcuts and techniques. There are 6 molecules which do not fall into these shortcuts. I'll give you the list of the 6 molecules once again. H3PO2, H3PO3, H4P2O5, H2SO5, H3PO5, HNO4. These 6 molecules are exception to the shortcuts that we are learning. You would have to be learning the structure of these 6 molecules on your own. So make sure you keep this point in mind. But for rest of them, you can use the shortcuts that we have learned here. And I'll also be giving you some molecules as your homework or as practice. So make a note of those molecules as well. You try and draw the structure of a few oxides using these rules, N2O4, N2O5, and also a few oxo acids like H2C2O4, H6Si2O7, and you can also try drawing the structure of H2S2O4. So take these molecules as homework and make sure you apply the shortcuts that you have learned and practice these molecules so that you grasp the concepts better. So this is all about this video. In this video, we spoke about how to draw the structure of oxo acids containing 2 central atoms. And I'll see you in one other video. Until then, bye.